Greetings, this is Mrs. Radigan with a lesson on zeros of real polynomial functions. We're going to talk about long division, the remainder theorem, synthetic division, and finding upper and lower bounds for polynomials. Just a little refresher on division. So remember, when we have a division problem, we have a dividend, and we're dividing that by a divisor. We get a quotient and a remainder from that. So the division algorithm says that if f of x is our function that we're going to divide by d of x, then we get f of x equal to d of x, the divisor, times q of x, the quotient, plus the remainder r of x, where x is either, or our remainder is either 0 or some degree less than the degree of the divisor. And we could write this in this way, or we could say that f of x divided by x divisor is equal to the quotient plus the remainder divided by the divisor. Okay, so let's do an example here of long division. So we have 2x to the fourth minus x cubed, and then I'm going to leave a little space, minus 2. We're dividing that by 2x squared plus x plus 1. So we're going to start by taking 2x to the fourth and dividing it by 2x squared, and that's going to give us x squared. We're going to multiply 2x squared by x squared, and we get 2x to the fourth plus x cubed plus x squared, and we're subtracting that, so all of those become the opposite. So we end up with negative 2x cubed and then a minus x squared. Then we're going to take negative 2x cubed and divide it by 2x squared, and we get negative x, and then we multiply negative x by 2x squared plus x plus 1, and we get negative 2x cubed minus x squared minus x, and we're subtracting that, so we do the opposite, and we end up with a 0 for both the x cubed and the x squared. We end up with a positive x, and then we drop down that negative 2 from the dividend, so we have plus x minus 2 over 2x squared plus x plus 1. So if we are to write this summary statement for this, we could either say that 2x to the fourth minus x cubed minus 2 is equal to the divisor times the quotient plus the remainder, or that function divided by the divisor equals the quotient plus the remainder in fraction form. If the only thing that we're interested in is finding out what the remainder is when we take some function and divide it by some expression, we can simply use the remainder theorem, which says if we plug in the solution to the factor, or the divisor, we will get the remainder that we would get if we were to take the function and divide it by the divisor. So we're going to take this divisor and we're going to solve for it. So if x equals 2, we're going to plug 2 into the function, and we are going to get, we're going to get 6. So that means when we take 3x squared plus 7x minus 20 and divide it by x minus 2, we get a remainder of 6. Similarly for this one, we're going to take x plus 4, set it equal to 0, so that means we're going to plug a negative 4 into our function. And when we do that, we end up with 0. Since f of negative 4 equals 0, we now know that x plus 4 is a factor of f of x, which brings us to the factor theorem that says a polynomial has a factor x minus k if and only if you plug in that value of k and you get 0 out of it. So if we were to look at this same problem, 3x squared plus 7x minus 20 from a long division standpoint, and we divide it by x plus 4, we would see that when we take 3x squared divided by x, we get 3x, which gives us 3x squared plus 12x, which we're subtracting, which gives us negative 5x minus 20. Then we take negative 5x divided by x, we get negative 5. We multiply negative 5 times x plus 4, and we get negative 5x minus 20. We're subtracting, and we're left with 0, which was the same remainder we got when we plugged in negative 4 into the function. So we know that for a polynomial function and a real number, k, if x equals k is a solution, then that is also a 0. It is an x-intercept, and x minus k is a factor of f of x. If you recall from last year, we did a shortcut method. It's only useful if your divisor is a linear polynomial, and you can just take those coefficients of the dividend. So we would take the 2, the negative 3, negative 5, and negative 12, remembering that if we're missing any terms, we have to put a 0 for a placeholder. Then we just take the 0 of the divisor, and we drop down the first term, multiply, add, multiply, add, multiply, add. This means that x minus 3 is a factor of this, and it means that these 2, 3, and 4 represent the x squared, because we started with an x cubed, the x, and the constant terms. So we can say that 2x cubed minus 3x squared minus 5x minus 12 is equal to this quotient that we got, 2x squared plus 3x plus 4 times the divisor x minus 3. When we look at a function, it could have rational zeros, meaning solutions or x-intercepts that can be written as a fraction. It could have irrational zeros, means zeros that are numbers like the square root of 3. It could also have imaginary numbers, solutions, which we'll talk about in another lesson. But if it has rational zeros, that means that those solutions are values such that the numerator of the solution is a factor of the constant in the polynomial, and the denominator of the solution is a factor of the leading coefficient in the polynomial. So for example, if we looked at x cubed minus 3x squared plus 1 and we look at the graph of it, we know that the only possible values for rational roots would be factors of 1, because that's the constant, divided by factors of the leading coefficient, where 1. So we could only have either positive 1 or negative 1, and if we plug either one of those in, we see that we do not get a value of 0. So that means these are not actually factors of this original polynomial. We can see by the graph that it's not crossing at negative 1 or 1, so this thing does not have any rational roots. When we look at this function, our p-values are going to be factors of 2, so plus or minus 1 or 2, over factors of 3, so 1 or 3. So our possibilities are going to be plus or minus 1 over 1, 1 over 3, 2 over 1, and 2 over 3. And if we look at the graph right here, we see that probably is the negative 2. And right here probably is going to be the positive 1. So we would try those using synthetic division. So we pick one of the roots to try first. It doesn't matter which one. We set up our synthetic division and run through, drop down the 3, multiply, add, multiply, add, multiply, add. We see we get 0, so that is a factor or a 0 of the function. And then we go ahead and use the second one, 1. We drop the 3 down, we multiply, we add, we multiply, we add, and we see we get 0. So that means our last root is 3x plus 1, or x equals negative 1/3. And we see that is a root here. So this one right here must be negative 1/3. So those are our 3 solutions to our polynomial. This is really the only new thing in this lesson that you didn't learn last year. So we can narrow our search for our real zeros using a test that identifies what we call an upper bound, or a number k that is an upper bound for the real zeros of the function. So this would be our upper bound, and a lower bound. So here's our lower bound, here's our upper bound. So if C is an upper bound and D is a lower bound, all the real zeros must lie within that interval from C to D. And the way we find those is by using synthetic division. So if f is a polynomial function with degree of n greater than or equal to 1 with a positive leading coefficient, if we divide our function by some linear factor x minus k, if k is greater than or equal to 0, and every number in the last line of our synthetic division is non-negative or positive, then we know that k is an upper bound. If k is less than or equal to 0, and the numbers in the last line of synthetic division are alternating negative and positive, then k is a lower bound for the real zeros of the function. So let's take a look at a problem that we use this for. So we're going to prove that negative 2 is a lower bound. So we're going to use synthetic division here. And we're going to make sure that these numbers are alternating positive and negative, which would say that it's a lower bound. So if we look at our synthetic division here, we drop down the 2, multiply, add all the way across, we see that we get a positive, negative, positive, negative, positive. So since the values are alternating, positive and negative, we can say that negative 2 is a lower bound. Then we want to check 5 as an upper bound, and we're going to see if we get all positives, which would mean it's an upper bound. So we go ahead and finish that synthetic division, and we see that we get all positives, 237, 49, and 253. Since those values are all positive, 5 is in fact an upper bound. Looking at the same problem here, we now know that all of our rational roots are going to fall within negative 2 to 5. So we set our window from negative 2 to 5, and we see if we can figure out what the roots are. So looking at our plus or minus p over q, our p is 8, our q is 2, so we have factors of 8 over factors of 2 and all those combinations. If we look at our graph here, it looks like 4 is going to be one of them, and then maybe negative 1/2 right here. Doesn't look like there's anything else. No 1, no negative 1, no 2, no negative 2, and no negative 4 and negative 8, because that's out of our boundary. So we're going to go ahead and use our 4 and do synthetic division. We see that we do in fact get 0 here. So then we're going to go ahead and use our 1/2 with the result of the last one. Again, we do our synthetic with negative 1/2. We get 2, 0, negative 4, 0. So negative 1/2 is a root. This means we have 2x squared minus 4 equals 0. If we go ahead and solve that, we get x squared equals 2 and x equals plus or minus 2. So our roots are going to be equal to negative 1/2, 4, and plus or minus the square root of 2. And that's it.